Good afternoon, everybody. I'm very apologizing you, but I have a problem, a technical problem with a colleague of mine, and so I had to solve this item. Good afternoon, everybody, and so today I will share with you another issue of this course on elasticity, and together we will face another point of our program in elasticity. Today we will start with static response issue. So we have the following presentation for everybody. I want to share with you my screen. Okay, and okay, and the item today is the item of the response issue. So after stability issue, we want to discuss the item of the aeroelastic response problem. And for aeroelastic response problem, I'm sorry, but I am scrolling our recent view graph in our whiteboard. And so I want to face with you today the first item on static response. And this is the item of the model for trimmed solution. And this probably is the most more clear and direct problem in elasticity. The scope of this item is to find a solution in steady condition for a trimmed aircraft. So you are flying, for example, with a straight flight, and you are flying with an angle of attack. So you are generating a lift, and this lift, together with the aircraft weight force, is actually deforming your aircraft, and therefore the aircraft is modifying the aerodynamics. And you want to know if this process, deformation, then load, aerodynamic load variation, then new deformation, new aerodynamic load variation, and so on, if this process will converge in a final trimmed solution. You want to fly with in trimmed condition, and you want a deformed configuration. Okay, and so we have to revisit some concept we had in the previously when we're talking about, for example, the boundary condition. If you remember, when we discussed the E1 matrix, development, the matrix or the operator transforming the Laplace Lagrangian variable Q in the set of normal wash, we avoid the influence of the steady contribution. But now we have to consider this, but we have also to include in the analysis also the presence of an angle of attack, a steady angle of attack assumed for lift your aircraft. Okay, so order, and we want to face this argument, dividing this argument in two parts. We have trimmed aeroelastostatic solution. And in order to better understand this modeling, we want to have first suppose to fix the angle of attack alpha, and this is the case of wind tunnel condition. When you have a wind tunnel, you have a wing in a wind tunnel. In a wind tunnel, you have a wing like this. You have a wall. This is the wall of the wind tunnel. You have an angle of attack, alpha, of your wing. You have your stream, and because of this angle of attack and this stream condition, you may have a deformation of your wing like this. For example, I want to be particularly dramatic and drastic, and this is the deformation. So we want to determine this deformation in the first problem, in the problem number 1, assigning an angle of attack and assigning a flow condition in a wind tunnel. So we don't want at first level to consider the flight dynamic trim of the aircraft. Okay, so the angle of attack is imposed. This is the story of wind tunnel condition. Tunnel condition means alpha imposed. This is not standard for an aircraft. For an aircraft, you typically one imposes the weight of the aircraft, and then one can evaluate the angle of attack and eventually the angle for the tail control surface delta in order to have a trim solution. In fact, at this level 1, we want only evaluate the deformation after this imposed angle of attack, and this deformation is obtained just imposing alpha and then evaluating the set of Lagrangian variable defining the deformation. Of course, these are not function of time in this case, but we have a static solution, and so we have a set of constant typically model constant, able to give us the steady displacement as given not function of time, but given as a combination of your model shape and the constant just evaluated. However, this is not the true problem. The true problem is to have a trimmed solution, trimmed configuration. So in the true aeroelastostatic trim problem, we have to assign the weight of the aircraft, the flow condition, and then you have to evaluate the angle of attack, the angle of the tail control surface for balancing your aircraft, and eventually the set of the Lagrangian variable giving us the deformed configuration. However, we want to emphasize this double step 1 and 2. Okay, so first step, impose alpha. We have our configuration, 0 angle of attack, and we have a normal vector defined on the body, like M. And then we want to consider what happens to this normal when you apply an angle of attack. You have that this configuration is rotated. Excuse me, my draw. Excuse me, my draw. Horrible draw. Consider a rotated configuration like this. So this normal is rotated in this way. Excuse me. And so we have a rotated normal and with an angle with an alpha normal correspond, and you have the original normal and 0 and the rotated one like that. Okay, and this is alpha. This is alpha, and this is alpha. Okay. So this is the situation as given by the rotation of the angle of the alpha in a side. In the other side, we want to redefine our normal wash condition, key, quantity in the normal wash in space discretized vision. And so key in the panel J, you have our panel and this is the panel J. In the panel J, key is given by the velocity of the body in the panel J, so in xj body, dot the normal in the panel J. Okay, and this quantity, if you remember, is given by a contribution given by the translation for having this velocity, plus a contribution given by the velocity of the deformation, the contribution of the deformation into the velocity of the body. So we have this, and this vector has to be multiplied with the inner product to the normal, and you know that we have the normal of the as obtained in the rigid body, remember, but you have also rotation, so we have n alpha plus a contribution given by the deformation. And so we have delta n alpha, if you remember, by, this is a vector quantity evaluated in the xj panel, by the model coordinate qn. And then higher order term, we don't consider this higher order term. So we have, in other words, the product of the velocity for the permeability condition. Here we have u, u infinite. I forget to write u infinite. So we have the flow plus the deformation for giving the total body velocity. So we have a rigid body translation plus the deformation contribution. And we have the rotated normal because of a rigid rotation for the angle of attack, plus the deformation on the normal given by, you have this here is rigid contribution, and this here is the elastic. We have already, this is the flexibility contribution. we have clearly evaluated this contribution, and I want to remind to you that this contribution is expressed in terms of cross product or edge product between the gradient of the mold shape. And this quantity are used for expressing the variation of the normal because of the elastic or flexible effect. Okay, so now we have to express the relationship here between the rotated normal and the unrotated normal for the rigid body. In fact, we have that the rotated normal indicated like N alpha in the XJ panel is equal to the unrotated 1 and 0 plus a contribution given by the rotation. If you see here, you see that the rotated normal is equal to the unrotated 1 plus this contribution here, this green contribution, and so you have that the rotated 1 is equal to the unrotated plus this green contribution, but this green contribution can be expressed for a linearized kinematic like the product between alpha and you see here approximately a vector, the green vector, which is orthogonal to the original normal. So we could express this vector like n minus n x 0, 0, excuse me, n zeta 0, n plus n x 0. In fact, the idea is the following. You have a frame of reference here, which is our typical frame of reference. We have the x-axis and the z-axis in the body frame of reference, which is the computational frame of reference. And if you want to express in a plane y equal to constant, which is the plane of a section of the wing, in this plane you can approximate a rotation of the normal just taking the two components in this plane of the normal, which are n0x and n0 zeta, and you can just to invert the component and exchange one of these for a sign. This is the old rule for obtaining an orthogonal vector in a plane. You may just to invert x with zeta in this case, and then exchange a sign in one of these. So this green vector is a vector orthogonal approximately. I say approximately because we are approximating this rotation motion. Okay, so we are approximating this rotation motion. So here we have an almost equal, and so we have the rotated normal is equal to the non-rotated 1 plus alpha by a fixed vector, and this fixed vector can be expressed like this green vector can be expressed like a vector equal to n1 function of xj. So at the end of the story, we have the following. We have that the rotated vector is equal to the unrotated 1 plus alpha, not a vector, excuse me, the alpha angle of attack by the n1 vector, where n1 vector is a vector orthogonal to n0 in the y equal to constant plane. Okay, so we have defined this rotated normal. The point is that we have expressed this normal as a linear function of the angle of attack. Okay, and so we can put this expression here inside our boundary condition now. Okay, let's go. And so we have that we have the following. We have that this key j is so, and I want to use a synthetic notation. Xj means key j function of in the point xj. So I want to avoid this notation, and so we have to take the product between this by this, and so we have minus I dot n0 u infinite, and then we have minus alpha I dot n1 u infinite. So I've just multiplied this by this, okay, and considering that this is equal to n0 plus alpha n1, okay, and so we have this term, and we have also plus, minus, minus, we have a summation of n from 1 to the number of panel, which is m, if you remember, and here we have q and I dot delta n by u infinite, and this contribution is the contribution of this multiplied by this, and next we have also a term like given by this quantity by the q dot quantity, excuse me, q dot quantity by n alpha, okay, but this term is 0 in steady condition, because in steady condition q dot is 0. However, for completeness, I report also this term here, and we have n from 1 to capital M, and we have q dot n by psi n, small shape, dot the n alpha normal, so is n0 plus alpha and n1 contribution, but this is 0, and therefore this term is identically equal to 0, okay, in steady condition. And so we can also introduce an undimensional normal wash, like key bar j quantity is equal to the dimensional 1 divided by u infinite, and then we can divide everything by u infinite. So simplifying this, and this, okay, and this here. And so let's consider what we have obtained at this point. We have that the normal wash in the case of a rotated wing, so this new boundary condition given by a rotated around the angle of attack configuration is equal to minus I dot n0 minus alpha angle of attack I dot n1 vector, which is the vector useful for expressing the rotation of the normal. Of course, this quantity is depending on j, on xj, and also this quantity is a local quantity depending on xj, okay. And here, as final contribution, we have this term, which is the equal to delta n in the point xj again dot I vector, this is a vector, and multiply by the Lagrangian quantity, giving us the deformation. So what are we expressing by this? We are expressing the uh, normal velocity as given by the body motion. And this normal velocity to the surface is given by the initial position of the panel. This is the contribution given by the initial position of the orientation of the panel with respect to the flow. Okay. In fact, we have this I, which is coming from the flow, and this M0 is coming from the normal to the surface. So you are giving an information on the orientation. So this is initial orientation of the panel. Orientation. Here you have the contribution in the rotated condition. So rotated contribution. And here you have the flexible contribution, flexibility contribution. So in other words, you have a panel like this, and this is the zero angle of attack configuration. So you have a flow, and you have a zero angle of attack contribution, then rotate, contribution of the angle of attack, and then deformation. Okay, so you have a final contribution to the normal wash given by the sum of these three separated contributions. Of course, we are in a linear regime, so we are currently summing each of this effect for giving the final boundary condition. Okay. Now, remember here what you have here. Here we have this quantity. You have this quantity here. Focus on this quantity. We have already studied this quantity. In fact, if you remember that the E1 matrix Jn element as a function of P, the undimensional Laplace variable, was equal in a steady, general unsteady condition, was equal to P, of course, psi model shape psi n dot n. This was the reference of normal in this case, by a length of reference minus delta n dot I. If you take your note, you can check this, and this was the expression of E1 boundary condition matrix. In this, if you take the steady limit case like P equal to 0, you have that in steady condition, you have that E1 0 Jn term is equal to minus delta n dot I. And this is exactly what we have here. So this term is the E1 matrix term for the term J is the index for the panel index, and N is the index of the mold shape. Okay, so this is E1, Jn, E1. Okay, and so we can rewrite our unsteady boundary condition in this way. Okay, we are ready. We are ready for rewrite together. Let's write our Lagrange equation of motion for our wing in the wind tunnel. But for steady case, and so we have the following: we have 0 by mass matrix apply to Q. So we have here S squared, but S is 0. So no inertial term plus kappa applied to our state space variable, but these state space variables are actually constant, representing the steady value of our problem. And here, this is equal to dynamic pressure, the E4 matrix, which is not depending on P or Laplace variable, E3 matrix, which is depending on P, but in this case, this is 0. So we have E3 matrix at 0P by E2 matrix at 0P. And here we should have the key vector, exactly the vector of the boundary condition, which are the input for our aerodynamic. Okay, so we have just to write this equation of motion. This is the static problem to be faced in the aeroelastic framework. Of course, we have to express suitably this boundary condition vector here. This is a vector. Remember, in the unstated general case, we expressed this key as equal in the Laplace domain, like E1 applied to Q. But now we have a generalized input, not the input of the flutter case, which was the input avoiding the steady part of the solution, but we are including also the part of the unsteady part of the solution. And therefore, we have just to write this quantity here inside our vector key bar. And do this together. And so we have K bar. Remember that K bar is the diagonal stiffness matrix in modal coordinate. Remember that we are using typically modal coordinates, and therefore the K-bar matrix is a diagonal matrix, like with the generalized mass by the omega n square quantity in the diagonal. So we have, we have m1 omega 1, m2 omega 2 square, and then all the other. So this is the 0, 0. This is a K bar matrix minus. Remember here that this key is composed by 3 parts, and we have the number 1 part, the number 2 part, and the number 3 part. So the number 1 part is E1 by Q. So if you have E4, E3, E2 by E1 on Q, you have the following. You have QD by E4, E3 at zero frequency, and then you have E2 at zero frequency again, and finally here you have E1, this E1 here at zero frequency as well. Okay, and so we have E1 at zero frequency applied to the state space vector Q bar, again here Q bar. Okay, so we have K bar on Q bar, and all these applied to the part 1 is giving to you the following. This is the part 1 giving to you this, and the product of these four matrix is globally the generalized aerodynamic force matrix here at zero frequency. Okay, but you have also the contribution of the term number 2 and number 1 and number 3. So we have the following. We have a dynamic pressure vector. You have E4, you have E3 at zero frequency, you have E2 at zero frequency, and then you have the other part of the vector of key. So one part of key is here, the other two parts are these two parts, number 2 and number 3. In particular, you have the number 3 part, and we can ask this number 3 part, depending on nj, as a unique vector. We may define this vector, excuse me, this vector red color, and we can define this as the vector f k with component fk0, so representing the steady contribution to the normal given by the initial condition in the J panel, and including the minus sign. Here, this other vector here, skip alpha angle, and this vector is defined like f k vector in the steady in the rotated condition component J. So at the end of the story, this 2 and 3 contribution can be summarized like a final vector f key 0 plus alpha f q1 vector. And these two vectors are known quantity, absolutely known quantity by the geometry of the problem. So look at this final problem. We can stop here, but this final problem is a very easy problem. You have the generalized stiffness matrix here. You have minus dynamic pressure multiplied by the aerodynamic matrix evaluated at zero frequency, and this matrix is applied to our model coordinate vector in steady condition, and this is equal to dynamic pressure. You have E4, all known quantity by the flow is 0, E2, 0, and then you have this special known term. Note that all this in the right hand side is a forcing vector. You know this vector because you know alpha. Okay, excuse me, I have And here we have the following. We have key 1 for but multiplied by alpha. So we have a known right hand side. This acronym is a general acronym for right hand side. And we have a linear algebra problem of type ax equal to b, and we have to solve this for x for q bar, and now we have just to invert this matrix here, and so obtaining our deformed configuration here, constant in time, of course, in this case, and this deformed configuration given by the modal coordinate vector is equal to k bar minus qd e 0 to the power minus 1, and then you have this right hand side, which is known whenever you assign alpha. If you assign alpha, you have a right hand side, and you have this problem. Right hand side. Okay, so this is the solution, the steady solution vector, solving the problem to determine the deformed configuration of a wing in a wind tunnel. You impose the angle of attack, and you have a deformation for the wing in the wind tunnel. Okay. Question for you. Question for you. Why I could have a not zero solution also in the case of zero angle of attack? In the case of zero angle of attack, you have this term is vanishing, but you have this term giving you a contribution in your right hand side. Is this possible? It can be justified, this kind of solution with a deformation with zero angle of attack or not? Do you have any answer to this question? Go. Is anybody?
Sorry, can you repeat the question?
Yes. We are actually solving the following problem. We are in the wind tunnel. We have a model in the wind tunnel, okay? And we impose an angle of attack to this half wing in the wind tunnel, and then turn on the wind tunnel. What I see is that this model may deformate in this way, and the deformation given in terms of modal coordinate, of course, these are steady model component, and I'm actually demonstrating that I can use modal coordinate also in the static problem, guys. Okay, this is not something strange. We can use modal coordinate also in static problem. Thank you. So we are turning on the wind tunnel. We have deformation. It's okay. You can evaluate this deformed configuration. Now, in the case with alpha equal to 0, you can do the same. You could obtain something not equal to 0 also in the case for alpha not equal to 0, because you have this fk contribution. Look, fk contribution here is arising from this term. This is the original one term. Excuse me. This is the original. Oh my God. Okay. We have the two term and the one term. So multiplying by alpha, we have. Okay. Multiplying by alpha, we have f1. So 2. Yes. The two term is this, and the one term is this here. The three term is this here. Oh, no, ho perso tutto. Oh. Excuse me, I lost everything. I lost everything. Oh, okay. So let's rewrite. We're the following. I'm going crazy with this distance teaching. So we have this equation at the moment. Oh my God. I've lost everything. I have K minus dynamic pressure, aerodynamic matrix, zero frequency on Q, and I have a right-hand side given by, again, dynamic pressure, E4 matrix, E3 matrix, 0, E2 matrix at zero frequency, and then we have an F0 vector, key 0 vector, plus alpha F key 1 vector, okay? So this, incredible, it's incredible. I have lost everything. Okay, this vector here is depending, is a vector not multiplying alpha. If you have alpha equal to 0, this term disappears, but you have this here. And so you may have a deformation also in the case of zero angle of attack. Okay, this is the right hand side. So in this case, with zero angle of attack, you may have a not zero deformation. Can you justify this or not? When you may have a deformation of the wing, also in the case of zero angle of attack. Is this physically possible?
For
yes.
a non-symmetric wing?
Right, yes. Not wing, airfoil. For unsymmetric, airfoil. If you have this at zero angle of attack, you may have a torsion because you have pitch moment, aerodynamic pitch moment. Okay, and this is the contribution helping you for representing this kind of solution. And in fact, this F key 0 vector is the vector built by the initial unrotated configuration, which may be such that to describe an unsymmetric airfoil. Okay, so at this point we have just conclude and satisfied this number one problem, and the number one problem was the problem of wind tunnel in wind tunnel. Next, in the next hour, we will discuss the solution in the case of trim configuration. Okay, just let's have a pause now together. I'm very sorry for the delay, for my delay. However, I will finish the lesson on time at 4 o'clock, but if it's okay by you, I will have together a break. Okay, thank you. Ovviamente ho anche una seconda domanda da porvi su questo problema lineare di statica che abbiamo trovato in elasticità statica. Pensateci, tanto vi faccio la domanda. I have a second question to give for you. Is this is let me share the screen. My question is the following. Is it possible to invert this matrix always? Do you know any kind of condition such that this matrix may not be inverted for solve our static elastic problem? Okay, this is the question. You have a few minutes during your coffee break for looking for a solution. A second for me. Guido? Guido, non ho fatto in tempo, sto nella pausa lezione, dimmi. Guarda, io finisco alle 4, finisco alle 4. È Guido, c'è anche Annalisa, stavamo ragionando, ho avuto una telefonata. Sì. Aspetta, ti invio, vai. Sì? Di.
No, secondo me lui quando dice si butta via il lavoro di 2 anni è una stronza, cioè voglio dire se il lavoro di 2 anni fosse stato
Dovevi sentire tutto quello che ha detto dopo.
No, perché ho fatto una telefonata con lui, era presente anche Annalisa e ha manifestato tutta la...
Un segreto io ovviamente.
Tutta la cosa che dici tu, cioè il fatto che lui sia astioso, abbia rancori repressi, che tira fuori anche in maniera pesante. Poi con me si sente libero perché glielo permetto di fare perché siamo d'accordo che ce lo facciamo tra di noi.
Meglio, così lo facciamo.
E rancore a 1000, Guido, rancore a 1000. Capito? E quindi lui...
Diciamo lì ci stanno alcune cazzate di fondo. Primo, legare tutto il lavoro fatto a una proposta che non è una proposta, perché la proposta è ok, cioè se ne sta discutendo nel gruppo.
Okay, so are you ready for this second step together? Okay. Do you have any answer to my question about the capability to solve this algebraic problem or not? I have, yes. Somebody wrote on the chat list for a u value such that k minus q e0 is a singular matrix. And do you know the exact name for such a u value? We have defined specifically this value. Do you know? Salvatore Riccobono told us a u value such that, and is there a name for this u value or not? Or is just a condition to be satisfied? Is anybody there? I can suggest you the solution. Look, we studied the stability, right? And in the stability problem, in the general stability problem, we have that here we have to solve the determinant of s square m plus k minus qd e s and u infinite equal to 0. And you may find u flutter and u divergence. For u flutter, your s here are typically complex conjugated, purely imaginary, like s plus minus j omega flutter. And in the case of divergence, you have a pole in the origin. And in this case, you have 0 this part and 0 here. So the value of u is the divergence. This is verified. The determinant is 0 in divergence condition. Where the divergence condition is a condition for a static, static, it sounds good, static stability. We are solving a static problem, and the condition for solving a static problem is to ensure a static stability condition. Okay? So let me rewrite. I don't remember if I have. Yes, we have to turn on the registration. So, the condition for having a algebraically static solution in our wind tunnel problem is to be free from having a divergence condition. Are you leading? Okay. But, oh, you're leading. Okay, okay. So, excuse me. So, now I want to solve the problem number 2. And for the problem number 2, we have the following. We have, for the problem number 2, we want to consider a free aircraft, free flying aircraft. So no wind tunnel condition. We have to consider, in this case, a weight of the aircraft, and we want to just to include to our problem one more Lagrange equation of motion. So we have, for free flying aircraft, we have excuse me, I can see the, okay. For the free-flying aircraft, we have the condition of weight assigned, and we have to determine a suitable angle of attack and the deformation set of Lagrange variable. Okay, so we want to trim, but this trim is very easy without tail angle, aileron angle. We have just to determine alpha, a suitable alpha for trimming our flight condition. So the solution is the following. Include a new unknown and include, in the meanwhile, a new equation of motion. The new unknown is the angle of attack. The new equation is the vertical rigid body motion. Okay? And in this vertical rigid body motion, for this new equation, the constraint is the following. We have to impose that the corresponding vertical motion is 0. So, in fact, we want to trim the aircraft. We want that the aircraft does not move vertically, but you have a weight balanced by the global lift distribution, but including deformation effect. Okay, effects. How can we do this? So it's not complicated, it's easy. We have just to consider we have to generalize what we obtained before. So we include in our motion decomposition, a zero model shape, so for n going from 0, so we have side 0 q0 plus the other, and this 0 is the rigid body motion. So this side 0 is just the vertical unit vector. Okay, 1. So a rigid body motion up and down. And the other flexible mode, but pay attention please, this flexible mode are the mode of the free structure, not clamped, not simply supported. No. This is the free structure mode. The first one, Q1, side 2, Q2, and the other. So first flexible motion means something like that. This is the reference aircraft configuration. And so the first mode is this: down, up, up, down. Okay, the red with respect to the black one, and all the other. Okay, so in this case, we have the following final problem. We have a stiffness matrix like this, 0. 0 is for the first Lagrangian variable associated to the rigid body motion. We have 0 modal frequency. The first mode of vibration corresponding to the rigid body motion is 0. So you have 0 here, and then we have m1 omega 1 square, m2 omega 2 square, and all the other mode. This is the stiffness matrix, symmetric, but the first term is 0, rigid body motion. Then you have to apply this, so you have n flexible mode and one rigid mode, the first one, the 0, the number 0, number 0, number 1, number 2, and so on. This is the rigid part. Okay, and next we have this matrix minus dynamic pressure applied to, and here we have the E01, E02, E03 element of generalized force matrix, and finally we have E0n, and in column you have E1, excuse me, we have before this we have indeed E00 term, and then E01, E02, and all the other up to E0n matrix. And this matrix is applied initially to the vector Q0, Q1 up to Qn. And at the end, we have as forcing term the same forcing term we had before. So we have E4, E3, E2, and then we have F key 0 plus alpha by F key 1, and attention please, we have also a known vector associated to the gravity load. In fact, we have that here we have external force. The external force are the weight force. The weight force is a field of constant. We have as load the weight, gravity, force in this case, and this is a force for unit mass of type minus k G as F force. Okay? When you want to obtain the generalized force corresponding to this, for example, the first generalized force is, and the second generalized force E1, the third generalized force E2, and the other, you have to take the integral on the body of your actual weight, which is minus kg, projected to the first mode shape, and here the same projected to the second one, the third, and here the E2 is equal to minus kg projected to the third one. But look at this mode shape. The first mode shape is a constant. This constant is, you have this shape for all the aircraft, a vertical translation constant as mode shape, and this is k itself. And so what is this? This is the density of the aircraft, of course. I forget the density for having the weight force per unit mass, okay, the density. And so what is this? This is the weight, equal to the weight. But here you have mode shape of the free body, of this type. You have to multiply this by this, for example, by this shape here, right? This is the first symmetric bending mode. So you have something balanced by definition. So this product between this mode shape with this constant field is identical equal to 0. So we are currently demonstrating that the constant gravity field, it is not able to perform work on the free mode shape of the aircraft. Okay, so what I say here is the following. In the right hand side of our steady equation, we have a term forcing the first zero equation, and all the other are zero. Okay, interesting. So in the case of for looking for a trimmed configuration, we have one more unknown. The unknown is alpha. This is unknown now. And look, the other unknowns are not n+1, because this Q0 is imposed to be 0. So we have 0 here, and this means that we can avoid this column. This column, the first column, is not relevant. We can just consider our block here, this block here. We can consider only this block here, which is n+1 row by n column. And we also, of course, not consider this column, the same block here. And at the end of the story, here your system, we have, in our system, we have n+1 unknowns, and we have the Lagrangian flexible model coordinate, only the flexible one, flexible model, not the rigid body, because the rigid body is imposed to be 0, flexible model 1, plus the angle of attack. And we have n+1 equations of motion, which are exactly this here presented. Okay, I want to invite you to to see the first equation of motion, the equation of motion associated to the rigid body motion. This equation is the following. We have a disaster. The equation of motion is the following. We have this zero, this not zero contribution, and this contribution here. Okay? And in the first equation of motion, the first equation associated to the vertical rigid body motion, the first equation of motion states the following. Zero elastic force. Of course, the rigid body motion is rigid, so we don't have any elastic reaction to our equation. Elastic motion, zero stiffness, zero modal generalized stiffness, elastic motion, plus, look here, we have this contribution, which is the contribution to the lift given by the deformation of the body. So here you have plus contribution to the lift force given by deformation, plus we have this third contribution. Let me complete this. We are analyzing this equation, the first equation. Okay, so this is the first contribution. The zero contribution is this here. We have this contribution, we have this contribution, 3, 4, this, and 5. We have the balancing of these 5 terms. The first one is the elasticity, and the elasticity does not exist in the rigid body motion. The second one is aerodynamic. You have to consider the contribution like this second contribution here is something like excuse me, is something like E0 equation first Q1 plus E0 second Q2 plus E0 3 Q3 plus ... the elastic contribution to the lift, to the first equation, elastic contribution to lift. Second term. The third term here is this here, is that involving F key 0. So this is the contribution to the lift given by the unsymmetry of the zero angle of attack, as you said before. For example, in the case you have something, and this is the contribution to the lift. This is the contribution, the number 4 is the contribution given by the angle of attack, and this should be the higher contribution. And finally, all this is balanced with the weight. So, plus or equal to QD, E3, E2, E4, excuse me, E4, E3, E2 by F key 0 plus the same QD E4, E3, E2, F key 1 by alpha and plus W. So this is the contribution to lift at 0 angle of attack, and this is the main contribution given by the angle of attack, and this is the weight. When you was a baby, you wrote L is equal to W. Now this is what you consider as W, probably as L, excuse me, these two contributions, but now we have also this contribution given by the deformation of the wing. But in a unique equation like this, you can linearly solve your problem of the trim, including the calculation of the angle of attack together with the elastic deformation corresponding to the weight that you have to lift. Okay? The last comment here is the comment on the final comment 3, but the real unknown, in a longitudinal trim problem for an aircraft is given by evaluating the angle of attack, right? The angle of attack, alpha, and also the aileron angle, the control surface of the wing tail, delta. Because we have to trim also the pitching degree of freedom of your aircraft. And this is the role of the wing tail, essential role of the wing tail. So the real problem is the problem giving you alpha, delta also, and finally in the elasticity, the set of Lagrangian variable. And so we have 2 plus n unknown. So we have to add one more equation. And so we have one equation for vertical rigid body motion. We have an equation for the elastic part. And we have one more equation here for, this is the novelty, for rotation rigid body motion, rigid rotation. The novelty here is the rigid rotation of the aircraft around the y-axis, so pitching. So we have to include one more equation now. Let's do this together as a final part of our lecture today. And I will conclude my lecture with this last contribution. So I would like to include with you one more Lagrangian variable in terms of psi -1. Let me use this negative index just to emphasize. I want to add a model contribution with so -1, and this -1 is essentially a rotation. So we have plus psi 0 as before for the vertical, so rotation, vertical contribution with Q0 plus the elastic 1 like psi 1, Q1, psi 2, Q2, and all the other elastic. So we have a vertical translation, and we have a pitch rotation here, rigid rotation here. So this Q -1 is a pitching angle of attack, like an angle like, I don't know, phi, okay, for the pitching. So at the end, we will have 0 quantity in the stiffness matrix, and then m1 omega 1 square, m2 omega 2 square, the elastic stiffness corresponding to the elastic free body deformation. And this here is the zero frequency translation, zero frequency rotation. So the first two equations here are the balance of the vertical motion and the pitching rigid motion. And again, we have minus QD, and we have something like -1E, -1, E -1, 0, E -1, 1, E -1, 2, and so on. Okay. And down here we have ER 0, -1, 0, 0, E0, 1, E0, 2, and so on. And vertically we have the other contribution. Like, for example, here we have E11, and here we have E10, and so on. Okay, but what I want to emphasize that these two metrics are referred to Q -1, Q0, Q1, Q2, but again, the first two variables are assumed to be 0. And so this column is not relevant, as not important. In this case, we have 0 here in the stiffness, in the model stiffness. However, this is equal to dynamic pressure, and please go in this other sheet, dynamic pressure, and here we have the list of E4, E3, E2, and the normal wash is now given by, again, the FK0, but pay attention please, we have FK1 by alpha, because the boundary condition is modified by the angle of attack, remember what we obtained before. But we have a novelty here, because in the same way we should define another suitable vector that we can name like K2 multiplied by the delta tail angle, like delta. And what is this? What is this? Let me complete, please. And then I comment this part. We have 0 in the load vector, but we have the W vector in the second equation of vertical translation. And question for you, aeronautical expert. Here, I should write the contribution of the aerodynamic to the pitch. So I should write here the aerodynamic moment. Excuse me, I should write here, excuse me, the contribution to the moment to the gravity force, to the gravity force. So the question is, what about the aerodynamic, the contribution of the weight onto the pitch, If you take a body in a space without air and leave the body to go down, is there any kind of moment of inertia such that, or any kind of moment which is able to rotate your body? No, because the final contribution is zero. So you have zero here for the gravity. And at the end of the story, you have two unknown, alpha and delta, plus your Q unknown here. And that's it. Q n by n plus 2 unknown in n plus 2 equations. A final comment on this. This vector is very, very similar to this vector here, and it is representing the capability to model the variation of the normal to the airfoil given by the angle of attack rotation. When you have a normal in the body here, you have a normal also in the control surface, and if you have a delta angle of attack, you can represent this normal variation in terms of delta by this quantity exactly in the same way you did for this vector here, delta Q1. So delta Q2 is just an extension of delta Q1 for representing the variation of the normal as given by the variation of the delta aileron, delta wingtip, tip surface angle of attack. Okay, so that's all for the aeroelastostatic trim. Next time, tomorrow, we will reconsider this equation. We have a wide comment on this, and see you tomorrow for the discussion of this model. Thank you.
Oggi sei preciso.
08.
08 che te costi, poi dici che ti scrivono. Ti scrivo perché lo sai così, altro che dici no, io sono sempre preciso. Senti, prendimi la...
Bye bye everybody, see you tomorrow. Bye.
Ah, sì.